All right, so time to start. So today's word is entailment, okay, that you see, and one of the topics that we are going to study today, and happen to be one of the most difficult topics in logic as well. Okay, so we will study this today, and after that, we will talk about soundness and completeness theorem. And if time permits, we'll talk about conjunctive normal form and disjunctive normal form. So today we are going to wrap up the first part of this course. So this course consists of roughly 3 parts, and propositional logic is 1 part. So we will be finishing up here. And the second part is the logic programming. So we are going to talk about this maybe starting from next. Okay. All right, so just repeat that today's word is entailment. Okay, so we have 2 open problems, and one is to prove the conjunction whether conjunction is trivial over disjunction and disjunction is trivial over conjunction. And here, the symbols that you see, this arrow is the two-way arrow here. This is the equivalence. And for those of you who remember, this equivalence means that when you apply the interpretation, their truth values are the same. Okay, so by definition of equivalence, what you have to show is actually their truth value result in the same when you apply every interpretation. So we are going to talk about this example. Actually, let me start with the review so that you can better understand. So we talked about a few concepts last time. One was the interpretation. Interpretation is a truth value assignment to the signature. Okay, so it's a function that maps each atom, like P to R, into either true or false. And once you have the interpretation, you understand how to you get the idea how to understand each symbol, each atom, whether it's true or false. And then you apply the this evaluation in a recursive way. So the way that we do is when you have a formula, we start with a formula, we draw the parse tree, and then apply the interpretation to the leaf node of the parse tree, and then do the bottom-up computation to find out the value of the formula, which is found from the root node of the parse tree. Okay, so given one interpretation and given one formula, you can determine whether this interpretation satisfies the formula or not by doing this calculation. And after that, we have this definition. When you say a formula is a tautology, then no matter what interpretation that you apply, you will always get true. Okay, that's a tautology. Satisfiability means that when the formula is satisfiable, it means there is at least one interpretation that makes the formula to be true. If there is no such interpretation, the formula is said unsatisfiable. And we can extend this definition to a set of formulas. So if you have a bunch of formulas, we say this set is satisfiable if there is only at least one interpretation that makes all formulas to be true. Okay, there is a common interpretation that makes all of them to be true, that is all satisfiable. The set is satisfiable. The last one is X, F is equivalent to G, which is crucial for these 2 problems. It's not easy to see, but it says that if for every interpretation I, the evaluation of F under I is same as the evaluation of G under I. In other words, their truth values are the same. Okay, so these are the problems that we will talk about. And is D7 ready?
If you imagine that these are all filled out, then they are.
Okay, then we'll start with D8. Okay, so D8. Okay, let me review what is the problem. The problem is about proof the Morgan's law. It's basically how to move the negation inside this parenthesis. Okay, so that's what part A is about. And part B is, can we find a similar translation for the Morgan's, like the Morgan's law? But now the symbol here is not a conjunction or disjunction. So suppose you have this formula, okay? Can you actually move somehow the negation inside the parenthesis? Same for this. If it has this form, can you somehow move this guy inside? Okay, so that's what the problem is about. Okay, let's see. So this is the definition, which is one-line definition. Typically, I find that about 30 minutes you need to look at this definition to really understand. The sentence is this. Entailment is about two mathematical objects. One is we are given a set of formulas called gamma, and another one is a formula, single formula f. And we say that gamma entails f if every interpretation that satisfies all formulas in gamma satisfies f as well. Okay? Okay, let me repeat. So what you do is every interpretation that satisfies all of the formulas in gamma must also satisfy f. Okay? If this condition is true, we can say gamma entails f. Now, first thing to note here is gamma entails f uses the same symbol as satisfaction between the interpretation and truth values. So there is actually the reason for this thing, but let me postpone the discussion later. Okay? Although we use the same symbol gamma here, what appears on the left-hand side is different. Before you had interpretation on the left-hand side of this symbol, but now we have a set of formulas gamma on the left-hand side. Okay, that's why the definition is actually different. This is also there's a terminology. When you have gamma entails f, we call f a logical consequence of gamma. Okay, so f is the logical consequence of gamma, meaning that if you so intuition is this: if you believe that gamma is true, then you have to believe f is also true. Okay, that's what entailment is about. It's entailed by this. F is entailed by gamma. F is logically following from gamma. If you understand that gamma must be true, then you have to also understand that f is true. That's what it's saying. So let's practice this definition. So first one, we have two formulas on the left-hand side. Okay? And for every interpretation that satisfies all formulas in the left-hand side, it also has to satisfy the formula on the right. So is this entailment true? Okay. So what are the interpretations that makes all formulas on the left-hand side to be true? What are the interpretations? A must be true, right? What about B? Yes. If A must be true, if you say the interpretation that makes A to be true, then and you also have to say that this interpretation I satisfies A implies B, meaning that A must be true, but since A implies B is true, B must be true too. Right? So in that case, the consequence B here is also true. Okay? So the idea is take any interpretation that satisfies all of them. There are actually two interpretations. One is the one that makes A to be true. Okay, there's only one interpretation. This interpretation that satisfies the formulas on the left-hand side, it must satisfy both A and also satisfy B. Right? A and B must be true. So consequently B is true. Okay? Now let's think about negative example. Suppose I apply the interpretation that makes AI to be true and BI to be false. Actually, you know what? Let's do this. So let's actually do this here. Okay. So suppose F is false and B is false. Okay? So this is the interpretation I. Does this satisfy this set? So this one, I, does it satisfy A? This is I that we are looking at. False, false. Does it satisfy these two formulas in gamma? Brandon? No. So this is false. So this is not. Okay? What about the next one? FT. Catherine. True or false? False. Why? A is false. It's the same reason. What about true or false? John.
False.
False. This one makes A to be true, but A implies B is false. And this one is actually yes. Okay, so I should say no. So this I, these first three interpretations do not satisfy these formulas, right? But the last one is the only one that satisfies it. According to the definition, you don't need to care about these interpretations, right? The definition is saying if the interpretation satisfies these two formulas, then it must satisfy the formula B. That's what the definition is saying. If the interpretation that you apply did not satisfy the formula on the left-hand side, you don't need to worry about it. You only need to worry about for every interpretation that satisfies the left-hand side, you should check whether it satisfies the right-hand side. Okay? So this is the only case that you have to really check for the entailment. And for this one, B is already true. So the answer to this question is true. Okay? Second one. Okay, I'm not going to do all the truth table here, but let's see. Is this entailment true or false? How many interpretations satisfies the formulas on the left-hand side? No, there's not one. Actually, two. That A makes A to be true, B to be true, A to be true, B to be false. So these two satisfies the left-hand side. Okay? But in either case, A or B is true. Because you already know that A is true, so A or B is true. So this is true. This entailment is true. Any question up to this part? Because we are going to have more examples. So if you don't get it, then probably you'll miss it, right? Any question? So it's funny there. Okay. All right. So the next question is this one. Is it true or false? Every interpretation that satisfies the formula A must satisfy A and B. Is it true? This is not right. Which one?
A is true, B is false.
Yeah, A is true and B is false. Satisfy this one, but not this guy. Okay, so this entailment is actually false. Good. What about this one? If you believe A is true, believe B is true, should you believe that A and B is true? Christopher, true or false? You don't know? Okay. Anyone else? Yeah? one interpretation that makes A and B to be true, right? So A conjunction B is true. Okay? All right. Now let's go into some tricky case. The left-hand side is the empty set. Okay? Empty set entails A or not A. This is true. So this is a bit weird case because there's nothing on the left-hand side. But what is the definition is saying? Every interpretation that satisfies all formulas in gamma satisfies this one, right? So if you have this interpretation, for instance, if you have false, false, does it satisfy every formula in empty set? Okay, so this is where your intuition is a bit misleading. When in logic, even when there's nothing to check, right? Every formula is actually being checked. In other words, there is nothing to check, right? So we can say if you see any formula, then of course you have to check it. But if you don't see any formula here, then this is automatically done. There's nothing to check. Okay? So one thing to be careful, every body, blah blah, doesn't necessarily mean that there is a somebody. Okay? Okay? Every Martian has to eat pepperoni pizza. Doesn't mean that there is a Martian. Okay? In logic, that's actually a bit different from the English use. When you say every something, doesn't mean that there exists at least one something. It could be the case when there is nothing. Okay? Every member of this set must satisfy this condition. It's also true when there is nobody in the set. Okay? So for this one, it might be a bit confusing, but if you understand the meaning of every in the mathematical sense, then all interpretations actually satisfies all formulas in the empty set. So then, what you have to check is whether all of the interpretations satisfies A or not A. And that is actually true because A or not A is a tautology. Okay? Or you can think about the other way. The definition is saying that gamma entails F. But what about the case gamma does not entail F? When is the case that gamma does not entail F? That's a complementary definition, right? When is the case that you can say gamma does not entail F? Let's actually think about that. So gamma does not entail F if there is okay? So first, I don't know whether you are comfortable to massage this definition, because this one actually requires the use of quantifiers in first order logic, which will be the subject later. But just to make sure that you understand, so when we say gamma entails F, it now becomes a matter of finding one interpretation that makes all formulas in gamma to be true, but not F. If you can find at least one such interpretation, okay, then you can say that gamma does not entail F. Okay? So for this problem, number 5, you cannot find an interpretation that satisfies all formulas in empty set, but does not satisfy tautology. there's no such interpretation. If you try to find an interpretation that does not satisfy this one, there's nothing. Okay, tautology is always true.
Okay, so having that in mind, now let's look at 6. Is that battery again? Maybe they have here. Okay. All right. So is this true? Empty set entails A. Can you find an interpretation that satisfies empty set but not A?
Just the empty set, even that one doesn't, because it's not a tautology.
So what is an interpretation that satisfies empty set but not A?
A is false.
A is false. Okay, A is false and B can be anything. But let's say A is false. Even if A is false, everything here is actually true because there's nothing you don't need to worry about, right? But then that interpretation that A is false does not satisfy this formula A. So gamma entails F is false. Okay, good. Now there's another tricky case. What about the case that we have one element in the left-hand side, but it happens to be false? The bottom. Bottom is always false, right? Okay? So is this entailment true? Can you find an interpretation that satisfies all formulas in gamma but does not satisfy this guy? Can you find one? Which interpretation satisfies the formula bottom? The interpretation. So say that we have A and B. Okay? Well, A should be what? Which one? Which one satisfies bottom? None of them. If none of them satisfies this one, what happens to the entailment? Entailment is definitely true because it says if every interpretation satisfies the formula here, you also have to check it. But if there is no such interpretation, then you don't have to check the right-hand side. Okay?
Sounds good.
So this is actually true because simply there's no obligation. Okay? So the obligation here is if you find an interpretation that satisfies all formulas in gamma, you have to check that interpretation satisfies the right-hand side, right? But if there is no such interpretation, then you don't need to worry about it. The entailment is so-called vacuously true. And let's actually go one more example and let's see what is going on. What about this A? Okay, so here the right-hand side is single formula A. It's not a given tautology, right? So is this entailment true or false? True or false? So again, the idea is if this interpretation satisfies this, then you have to also check whether this interpretation satisfies this one, right? And you can do this for each of the interpretations. Okay? For each interpretation, for every interpretation, this condition is true, then you can say this entailment is true. If you find at least one interpretation that happens to make this to be true but not this guy, then you can say entailment does not hold. Okay? So let's check it. Does false satisfy this? Bottom. No, bottom cannot be true, right? So you don't need to worry about this guy. What about false true? Does it satisfy this? No. True false? No. True no. So you don't need to even worry about what is on the right hand side. Okay, so this entailment is actually true. Okay, it's a bit similar to the bottom elimination rule that you saw before, right? So from the bottom, you can derive any formula. In fact, bottom entails any formula too. Okay? And even the bottom. So bottom actually entails bottom too. Okay? Because simply you don't need to worry about the right-hand side if there's no interpretation that satisfies the left-hand side. Okay? So even this guy is true. What about the last one? A or not A? So now, if this interpretation satisfies A or not A, you also have to check this guy, right? So let's do one by one. False, false. Does it satisfy this one? Yes. Does it satisfy this? No. So what do you conclude? Entailment is false. You don't even need to go to the other things, right? Yes.
I don't know if it's one of your examples coming up, but you say that bottom entails top. What is that?
Bottom entails top. That's a good example to use. Actually, I use up all my example here. So let's think about it. Bottom implies top. Is it true? Obviously, right? Because I said for the bottom you can entail any formula, including top, bottom, A, whatever the frame top. On the other hand, I don't know whether you have noticed this. If the empty set entails some formula F, what should be this formula F? F has to be a tautology. So what do we have? So these two, right? For this entailment to be true, we see this is the tautology. If it's not a tautology, entailment doesn't hold. Why? Because for this one, you have to try all interpretation, because all of the interpretation satisfies the empty set. So you have to check this one. Okay? So when this is empty, you always have to check the formulas on the right-hand side. When left-hand side is bottom, you don't have to check anything on the right-hand side. Okay? All right, so that's good. And here's an algorithm to check the entailment. Okay? So to check that a set of formulas entail a formula F. We already talked about this. Let me just write in the algorithmic way. So what you do is for each interpretation I, you see that whether this I satisfies each formula G in gamma. Okay? So for each of the formula in the gamma, you have to check whether I satisfies that. Now, there are some cases that the I that you started with does not satisfy all of the formulas on the left-hand side. Then you don't need to check the formula on the right-hand side. So you just continue to next interpretation. However, if you find this I satisfies all formulas in gamma, then you have to check whether I satisfies F. Now, there are actually two outcomes. When you check the formulas on the right-hand side, if it is yes, that doesn't actually tell much about it, because it simply means that we didn't find a counterexample for the non-entailment. So you just continue to next interpretation. However, if you are in this case, that means the interpretation that you have I satisfy all formulas in gamma, but not the formula on the right-hand side. That means the entailment is false, so you don't need to go further. Just stop there and report that entailment is false. Now, once you do that, what happens is either you may stop at some point, okay, and return not entailed, or you exhaust all interpretations, meaning that you couldn't find any counterexample for non-entailment. So when you exit all of these loops, then you will be out of the loop, and at that point you can say that entailment is true. Okay? So which one is quicker? So if you're lucky, then you can find out not entailment during the middle of the computation. So you can exit there. But if you want to say this is entailed, then you have to exhaust all interpretations. Right? This one? No? All right. So obviously this contains loops, right? So nested loops is not an easy computation, okay? But if you need to do by hand, but of course computers can do this for you. Okay, now, oops. Now let's now come back to this training example. Okay, we already have proven this fact using natural deduction, but now let's talk about this entailment. What we say is, if you have this set on the left-hand side, okay, then this set entails taxi at the station. In other words, if you find any interpretation that satisfies all three formulas on the left-hand side, that interpretation must satisfy the formula on the right-hand side. Okay? So how many interpretations do we have to try in the worst case? In other words, truth table. We are going to draw truth table as we did for the D7 and D8. 8. Okay, so let's draw the truth table. False, false, false. Okay. Now you will realize why did I ask this kind of enumeration question in the test, right? A lot of time you have to enumerate these things. Okay, so we have to find interpretation that makes this formula to be true, okay, as well as this formula is to be true, as well as this formula to be true, okay. So I can draw all these things, but let's try to use some shortcut, okay. So when is the case that TL is true? TL is true only for the last four interpretations, right? So this is true, 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 true. So we can only look at this guy, right? And when is the case that JL is true? I'm sorry, negation of JL is true. Okay, when JL is actually false, right? So let's actually write everything. Okay. So this is opposite. So TF, 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 TF. Okay. What about the one on the here? Okay. So I can actually write everything, but actually I don't need to do, because what I need to find out is the interpretation that satisfies all three formulas to be true. So this is hopeless, right? Because TL is false, and also this is hopeless because not JL is false. So I only need to focus on these two. Okay? Now let's check this interpretation. For this one, is this formula true or false? This is false, right? Because TL is true, not T is true because of this is false, not T is true, and this is false. So it's true implies false. So this is actually false. What about this guy? True and false implies false is true. So how many interpretations make all three formulas to be true? There's only one. This is the only one that makes all three formulas to be true. Right? I mean, if you want, you can also draw all the tables. I'm just using some shortcut to claim that this is the only interpretation that makes all three formulas to be true. If you can do in any way, like writing the whole table, I'm okay. Okay? But this is the interpretation that makes all formulas to be true. Does this satisfy taxi? it does make X to be true. So what do you conclude? Does entailment hold? Yes. So this entailment is true. Because you can do this in a normal way. So take each interpretation and check whether this satisfies all three formulas. The answer is actually no. Okay, go to the next interpretation. Okay, and check whether this interpretation satisfies all three formulas. That's also no. Same for this guy, same for this guy, same for this guy, same for this guy. For this one, it makes all three formulas to be true. Then now you also check whether this interpretation satisfies T. Yes, it is. So we go to the next interpretation, and here you see that this one does not satisfy all three. Okay, and then you exit the loop, and you report entailment. If you're not clear about what I just said, just compare with the previous algorithm and do one by one. Okay, so you will see that the entailment is true in this case. All right. So now let's talk about the relationship. Okay. So how are tautology and satisfiability related? Any idea? So tautology, when you do the tautology, we have some exercise problem. Okay, so how do you find that this is not a tautology? Okay, and also how do you find that this is satisfiable? So to check this is not a tautology, what do you need to do? So to find that some formula is not a tautology, you need one interpretation that makes the formula to be false, right? And to find that whether the formula is satisfiable, you also need one interpretation that makes the formula to be true, right? Okay, so what is the relationship? A set is not satisfiable if and only if its negation is a tautology. Right? So when you say that set is unsatisfiable, that means there is no interpretation that satisfies all formulas here. Okay? So let's look at the example. Suppose you have P, Q, and not P or not Q. This set is not satisfiable. So this set is not satisfiable, right? Because there's no interpretation that makes this to be true. And you can check that this is also true. Okay? So on the left hand side, you cannot find any interpretation that satisfies all formulas to be true. On the right hand side, if you compute the negation of the conjunction of three formulas, this is always a tautology. Okay? Well, this is actually same as P and Q right? If you just flip the negation, right? Negative formula is a tautology, means that the original formula is always false for all interpretations. Okay? If it is always false, that means there is no interpretation that satisfies all three formulas. These two are if and only condition. You can also write this in a different style because one of the things that we learned before is P is equivalent to Q is actually same as not P is equivalent to not Q, right? So you can flip this one, is unsatisfiable to satisfiable, and
is a tautology to another tautology. Okay? So these two statements are actually the same statement. It's just written in a different way. Okay? So in other words, the set becomes satisfiable if this one is not a tautology. Okay? Any question about this? So, the satisfiability, tautology, okay? So they are related concepts. How do you relate? When the set is unsatisfiable, means that the negation of their conjunction is actually tautology. And vice versa. Alright, the next one is how entailment and tautology are related. Okay, so this is the relation. Maybe you have guessed it when we are doing the examples. So F1 through Fn entails G if the conjunction of F1 through Fn implies G is a tautology. Okay, so here is an example. If you have P or Q as F1 and not P or Q as F2, this entails Q, right? Okay, and this is same as saying so P or Q, or not P or Q, to be true, you have to have an interpretation that makes Q to be true. So this entailment is true. And on the other hand, if you have P or Q and not P or Q implies Q, you can check that this is also tautology. Okay? Now, when you have if and only if condition, that means it doesn't mean that both of them are always true. Both of them can be false, and they still make if and only if to be true. So, for instance, if you change the formula on the right-hand side, okay, P or Q, comma not P or Q, does it entail P? Does P or Q, not P or Q entail P? Can you find an interpretation that makes the left-hand side to be true but not the right-hand side? P is false? P is false, Q is false? P is false, Q is true, okay? Makes the first formula to be true. Okay, just pick out one interpretation. Which interpretation should we do?
Well, are you trying to make P true or false?
P to be true?
Oh, the first one satisfies that.
Okay, so let me get back. So we want to check this claim, okay? There are 4 interpretations possible, okay? And can we find an interpretation that satisfies the 2 formulas on the left but not on the right? If you're stuck, you can always enumerate everything. So we can have false, 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 true, true, false, true, true. Does this satisfy these 2? Does false, false satisfies 2 formulas, P or Q and not P or Q? True or false? Okay. So false or false is false, right? So this formula is false, so the whole set is not satisfied. Okay? So this does not satisfy this one. Okay? What about this? false true. Yeah, so this one, false true. False or true is true, and true or true is true. So this is actually true. So this P is false, Q is true, satisfies the formulas on the left hand side. Okay? Does it satisfy the formula on the right hand side? No. So entailment is false. Okay? And same way, you can see that it's not a tautology. How do you know that? Apply the same interpretation. P is false, Q is true, and you will see that this formula is not true. Okay? Yes?
Shouldn't be implies P at the end is not.
Oh yes, you're right. Thank you for correction. This should be actually P. Yes. Yes. Copying it. Okay, thank you. All right. The special case. So one special case here is the last line here. So when left one is empty set, right? Entails G. Okay, G must be a tautology. Okay, we talk about this when we do the examples, right? Empty set entails F means entails G is same as saying that G is a tautology. Good. All right. Last slide. How are entailment and satisfiability related? Okay. So this is the relation. So let me actually give you an example. As we just saw in the previous slide, this entailment is true. And you will see that this is actually same as saying this set is unsatisfiable. Okay? Why? Well, entailment means that everything, the interpretation that satisfies everything must satisfy this one, right? So if you flip it, then you cannot satisfy all three formulas. Okay? So even if you find an interpretation that satisfies these two, okay? If this is unsatisfiable, means that this is false. Okay? Then its negation must be true. So I gave some examples and to give you some intuition, but formally you can also prove why this is the case using the definitions. Okay? All right, any question about